So internally, the PLCs can do a lot more than hardware devices. So once they got past the replacing relays, which is basically contacts and coils, in fact, they kept the nomenclature. The C bits are what they call a coil. We have what's called a coil, and most of them, they use a C as the indicator for that. And once we got past the original ones, the early ones, in fact, some of the ones I worked with only did digital, and then they had instructions to handle numbers, but they were very crude. It was things like load a number into a register and then add another number to that register and put it in another register and then use that register to do something else. So what's come along in the meantime is that they have made function blocks as part of the PLC programming. So here we have a timer function block, right? And it's represented as a block, and it has an input that starts the timer, has a preset value, and it runs. And then there's, right below it, we have another one called stream out, which is sending data out to a device. And you just have to plug in a few of the parameters and it works. So this replaced what would have been a long ladder program of moves and loads and unloads and copy and do all this stuff that we used to do. So this has made so we have stream out, we have stream in, right? And these are blocks that you just pull out of the toolkit and you plug them in and you supply them with the correct data and they handle it. When they're running, they show a lot of the data that's changing and so forth. Okay, so this makes gives us tremendous capability. We now have this PLC happens to have very high speed inputs and outputs. We can input a signal up to 250 kilohertz, and we can output a signal up to 250 kilohertz. So the machine that this is going in, our input is, we're actually using only one digital input, which is something called PWM, pulse width modulation, but we have an 80,000 hertz rate of going out to drive the servo forward and back. So this is able to do motion control without another motion control device. So as I said, this is the name Do More really is true. It's got a lot of capability. And so we're using the same unit. This has 3 channels of high-speed input and output. So we can hook encoders up. And in the case of the one machine, the Woody that we built, we had encoders on the motors, and we got positioned with a regular motor by feeding back into the high-speed input and then using that to tell the motor where to go. So it's all perfectly capable. The biggie difference between PLCs and hard wiring, in the case of the hard wiring diagram, 2 things can truly happen at the exact same instant, okay? Meaning that 2 switches could close and could be in exactly the same instant that they closed, right? In a PLC, that's not true, all right? And the reason is, the way that a PLC program works is everything is done on scan. And the scan is very simple. And this particular PLC has their code organized this way. They have what they call top of scan. So top of scan is all of the inputs are in the top of scan. So the PLC doesn't actually make anything happen until the entire program has been read over and over and over again, okay? So the first thing it does is it reads all the inputs and then goes down through all the code, evaluating the code, and comes up with an output table. And then at that instant, it turns on the outputs, okay? So this scan cycle you have to be aware of. And as the PLCs got faster, we stopped worrying so much about the scan time getting real long. It used to be common that you had to play some games sometimes because the scan time would get too long, and then a button that you wanted somebody to push might get missed because it took too long. And now that's no longer the case. The scan times are usually fast enough. Plus, this PLC uses a method of coding. It uses both stage and subprograms. When a subprogram is off because it's not being used, it isn't on scan. So it isn't wasting time reading any of the code that's in that subprogram. Same thing is true of the stages within a program. And stages are a way of doing things sequentially. When you have a stage sequence going on, the stages are typically going on one at a time. And what that means is all the stages are off scan except the one that's currently active. And that saves a huge amount of scan time. Okay? So the consequence of the scan is that things at the top of the program can always take the stuff at the bottom takes precedence. In other words, if I say turn on this light at the top, and then I go down in the middle of the program and say, turn it off, turn it on, turn it off, turn it off. The last one wins every time. Because it scans and it evaluates everything and comes up with the answer, and then it makes the outputs change. Now, the typical scan time is a millisecond or less. So it's like 1,000th of a second, which is usually perfectly fine. On top of that, sometimes you have stuff that is so fast the scan can't catch it. So there are some codes that are immediate instructions that say, when this happens, do that right now. Don't wait for the scan to complete, do it right now. I almost never use it. I don't think I've ever, I think I've used one only one time in my career, because most of the time the scan is fast enough not to be a problem. But the important thing to remember is that because of the scan, and two things cannot happen together, there's also some advantages. Like, for instance, I can evaluate a number and then immediately underneath of it change the number and then change it again and then change it again. And I don't have to write code to say, oh, well, if this, do that. Because what happens is the precedence, the thing I want to be most important goes at the bottom. So like in the case of messages, when we put messages up on the screen, we have alarm messages. The messages are in sequence in the code by precedence of what is the most important. So like the least important is the first message and the most important is the last message, because that message will always happen. When we're sending out the code to the HMI to put up the message, it's the last one that's active that always it shows up. And I don't have to turn the others off or do any of that. It just happens. Okay? So this is how the PLC, does its thing. The scan is and this is true of all PLCs, all right? The scan. Now, if you compare a PLC to a PC, Windows is non-deterministic. What does that mean? Well, Windows can't really do timing correctly, all right? Because it's non-deterministic. You know how sometimes your mouse stops moving. You can't do that in the real world of machinery. You can't suddenly have a saw blade turn off while the saw is moving forward, right? And that's the non-deterministic nature of Windows. That is why it's not widely used as a control program, right? And whereas in a PLC, it's absolutely happens every single time. And over the years, I've had people say, "Oh, the PLC is doing something strange." No, so far I've never seen one doing strange. All right, it's always something that's not working the way it used to to be, and it's not the PLC. It's like, you have a switch that no longer makes contact all the time, and they say, the PLC is not seeing that switch. The switch is not working. It's not the PLC. It's just, and part of that is because part of the scan cycle is a whole bunch of error checking that you don't realize is going on. Like, for instance, they use what's called a cyclic redundancy check. And basically what they do is, whenever they have time, they add up all of the bits in the memory, and they compare it to a number. And if it doesn't match the number, something changed, like a bad memory thing. So even if you had like a single bad memory chip, or a part of the processor went bad, the PLC would find it and throw an error. I can tell you, I haven't seen those kind of, I think I've seen it one time where I had a PLC that was bad that way. More common failure on PLCs is like blowing up an output or an input from somebody putting voltage to it that doesn't, that's more than it's supposed to be. But as far as the failure rate on the PLCs, it's really, really low. So us programmers are way more responsible for the problems with PLCs.